Welcome everyone to this week's webinar. Get your calculator ready or just enjoy the ride as we take the TI-30XPlus MathPrint calculator to the limit. In this session, we'll look at differentiation from first principles. We'll use a combination of function notation along with stored variables and the table feature. Next, we'll look at the approximate area under a curve. In here, we'll look at left and right bound or inner and outer rectangles, trapezia or trapeziums, and we'll also have a crack at Simpsons rule. Finally, we'll take a look at a range of limiting sums. You'll see how we can use this to build an even greater understanding of both differential and integral calculus. So let's get started with differentiation from first principles. Here's a graph of the function f of x equals x minus 1 all squared over 4. Suppose we are interested in the gradient when x equals 3. The tangent line shares the gradient of the function at the point of contact. So in our case, at x equals 3. We can draw a secant line, a line that crosses the graph at 2 points, and see that it has a gradient very similar to the tangent, depending on how far apart those 2 points are. But we can at least use it to approximate the gradient of the tangent. So, that's a simple application of rise over run. Let's see how to do that on a scientific calculator. So, we'll start with a vinculum or fraction tool, and we'll substitute our numbers in. I'll get the calculator to do all of these calculations. So we'll substitute 4 in for x. So our equation is x minus 1, so 4 minus 1 squared over 4. That's the first point, minus our second one, which is at 3 over 4, and the run in this case is just 1. And there's our answer. So we could say the approximate gradient of the tangent is 5 over 4 or 1 1/4. Now, what if we make those 2 points a little bit closer together? So instead of making the second point at 4, make it at say 3.5. I could type all of that over again, but on our calculator we can just go up, select it, press enter, and that will paste it straight down. So I need to change the original substitution of 4 to a substitution of 3.5. I'll use the insert key, and I've got 3.5, and I'll divide it by 0.5, the new run. Press enter, and we see the gradient is approximately 1.125. The calculator has the ability to define a function. Press the table key, select option 1, and we can store our function in here. Our function is x minus 1 all squared over 4. So I'm going to use g of x later, but for now I'll just quit from here. So instead of doing the substitution like we did before, we can make it a little bit more natural now. I want to calculate f of 4. So press the table key, select option 2, we substitute in 4, minus f of 3, and it's all over 1. We've got the same answer as before, of course we do. It's just a little bit quicker to edit. So now if I go back up, I can copy and paste this down, and let's change the 4 to a 3.5 like we did before. Again, I've got to swap into insert to put it in there. And our run is 0.5. And we get the same answer as before. It's just a little bit nicer notation and a little bit quicker to do so. But let's go back to the graph and see if there's a better way we could do this. If I look at the distance between the two x coordinates, the horizontal distance, I'll say that's equal to d. So therefore, we can say the approximate gradient is equal to f of x plus d, that's the point on the right in our diagram, minus f of x all over d, where d is some arbitrary distance. And as d gets smaller and smaller, we get closer and closer to the gradient of the tangent. Can I use the d and the f of x on my calculator in the same way? Let's have a look. Recall, we're finding the gradient when x equals 3. So I'll start by storing x as 3. And I'm going to use d, so I'll store that as 1 just for now. I know we've done that one before, but just so we can check our calculations. And now we'll write the expression, like we saw on the previous page, f of x plus d minus f of x all over d, and we get the same as what we got before. But now it's much quicker to continue exploring. I don't need to change the value stored in x because we're exploring the gradient when x equals 3 as d gets smaller and smaller. So I just need to store smaller values in d. So let's store 0.1 in. And now if I go back and get that calculation, it will redo it with our new value of d. So I see the gradient's about 1.025. Let's make d even smaller, 0.01. We'll store that in d. Retrieve our previous calculation. And we can see it's definitely approaching 1 now, 1.00. Let's go really silly. Let's go really, really small. And we'll store that value in d. And go and retrieve our calculation. And you can see the calculator says it's about 1. It can't store that many decimal places. So, what if I change the value of x? What if I wanted to have a look at the gradient of the function when x equals -1? So let's try -1. We'll store that in x. Now I don't have to change d. I've got d as a really, really small value. So let's see, what would the gradient of the function be when x equals -1? Gradient's -1. What about when x is, say, 0? The gradient's -1/2. Now, we could go through and continue calculating these, but again, there's a quicker way. You remember we had another function, g of x? Conveniently, we'll call it gradient of x. So I'll press table. I want to add or edit the existing functions. F of x is staying the same. So let's make g of x equal to our general function for the gradient. So that was f of x plus d minus f of x all over d. And now we can get the calculator to generate a table of values. Let's start, say, at -1. We'll go up in increments of 1, and we'll get the calculator to automatically generate the table rather than asking for specific values of x. And there's our table of values. That's pretty quick. So we can see when x equals -1, f of x equals 1, and the gradient is approximately -1. When x is 0, the gradient, or the function rather, is 1/4, and the gradient is about -1/2. This other value for the gradient, that's approximately 0. And then when x equals 2, the gradient's about 1/2. When x equals 3, we saw the gradient's about 1. The gradient appears to be going up by halves. We could plot those points on a graph. So we saw from our table of values, when x equals -1, the gradient was about -1. And when x equals 0, the gradient was about -1/2. And at x equals 1, the gradient was 0. And so we plot a function that represents the gradient of f of x. I think we could be confident in saying that's a linear function. So, using the calculator to differentiate from first principles, we can see that it's very efficient. In fact, if I wanted to explore another function now, I just change my definition of f of x. I've already got g of x, our gradient function, defined. We can use natural function notation, which makes it a little bit easier to use and of course is easy to generalize. So let's have a look at integration, that is the approximate area under a curve. We'll use left and right bound or inner and outer rectangles. That depends on the curvature as to whether or not those two things are the same. We'll have a look at the trapezoidal rule and we'll have a little crack at Simpsons rule. So this time we'll make our function just x squared on 4. We'll determine the approximate area bounded by the curve, the x or horizontal axis, x equals 0 and x equals 4. We'll start by using right-bound rectangles. That is, the rectangles that we're using are bounded by the curve in the right-hand corner. And in this case, because of the curvature, that's exactly the same as what we call outer bound. So the first rectangle is bound by x equal, or when x equals 1. The next one would be bound on the right-hand side at x equals 2, then x equals 3, and x equals 4. We can work out the area of rectangles pretty easily, because if we know the height, which is just f of x, and the width, which I'll call delta x, we just multiply those two things together and add them up for each rectangle. In other words, we calculate the sum from x equals 1. Now it's x equals 1 because that's the height of our first rectangle, f of 1. All the way through to f of 4, the height of our last rectangle. So we will sum up those 4 areas. Height, f of x, by width, delta x. Let's see how we can do that efficiently on the calculator. So I'll quit back to my home screen. I need to go in and edit my function. We've changed our rule. We've just turned it into x squared over 4. So I can just delete off the bits that I don't want rather. I can delete that one now. I'm not going to use that. And then I can quit back to my home screen. Now, the sum tool is in the Maths menu. It's towards the bottom, so I'll hit the up arrow. And there it is there, option 5, sum. Press enter. And we want to sum from x equals 1 through to x equals 4. We want those values substituted in to work out the height, in other words, f of x. And I could do multiplied by the width of 1, but that's not going to make any difference to our answer. So we can just press in enter. And we see the approximate area under the curve, an overestimate, as you could tell from the diagram, is about 15 over 2 or 7.5. Let's go back to our graph. There is another way we can calculate the approximate area under a curve. We could make the rectangles bound on the left-hand side. You'll see that the height is defined by where the rectangle would hit the left-hand corner of the rectangle. And these we also refer to, because of the curvature, as inner bound. The area under the curve that we get this way is going to be less than the actual area. And in this case, the height of the first rectangle is defined by x equals 0. Then x equals 1, x equals 2, and then x equals 3. So we want to sum the areas of the rectangles from x equals 0 to x equals 3. The height multiplied by the width. We can do that pretty quickly on the calculator by simply going back, pressing enter to copy and paste, and we just need to change that 4 back to a 3 and the x here down to a 0, and we're done. So an underestimate, the left-bound rectangles, is 7 over 2, or 3.5. I wonder if we could improve that estimate a bit further. We could use trapezia, a series of trapeziums. So the yellow area, sitting kind of in the background, was our right bound. Then the red columns represent the left bound. If we averaged those two results geometrically, we actually get a series of trapeziums, or plural trapezia. So we can just average the two calculations that we did before. Let's see if we can do that efficiently on the calculator. I'll use a vinculum, and let's go and retrieve our first calculation. And I could just retrieve the answers, of course, plus that one all over 2. And we get an average of 5.5. So keep that in mind, maybe write it down somewhere. Our estimate for the area is about 5.5. That's using the trapezoidal rule. Now we said we'd have a crack at Simpsons formula, or Simpsons rule. So let's have a look how that works. We'll start by looking at the rule. It looks kind of ugly. Integral from x0 to x2, where x2 is equal to x0 plus 2 lots of h. Well, our h is kind of like the width that we had before. And it says that the area is approximated by h over 3, 1 serving of f of x0, 4 servings of f of x1, and 1 serving of f of x2. Let's see that on a diagram. So there's our height of our first object, we'll call it, f of x0. Then f of x1 and f of x2. They're the values that we need to be substituting into this rule. And in this case, if I'm going from, let's say, 2 to 4, and we'll do our whole area in a short moment, but let's just do this one, h would be equal to 1. So we'd have 1/3 and then all of these things. So let's do that area. That'll be that spot there. And then we'll do another calculation from 0 to 2, because it's important to see how that all works. So I'll jump back to my calculator. I'll clear off those calculations. Now our width, we said, was 1. So the formula had us doing 1 over 3 multiplied by, and if I'm doing the area from 2 to 4, then I had to calculate f of 2 plus 4 helpings of f of 3 plus 1 helping of f of f4. So it says the approximate area between 2 and 4 is 14 over 3. Now, I can do the same for the area between 0 and 2. Then I can add those two results together. So I'll go up and copy and paste that down. So that one becomes a 2, that one becomes a 1, and the other one becomes a 0. And now all I need to do is add those two areas, that one, or I can do that one plus that one. Oops, I did multiplied. Let's fix that. We'll do that one plus that one. And we get 16 over 3. Interesting. If you do use calculus to work that area out, it's exactly 16 over 3. So Simpsons rule has given us the exact area. That's because Simpsons rule doesn't use rectangles or trapeziums. It actually approximates the curve, that line between the two, it approximates it as a quadratic. And because we're using a quadratic, in this case, it's actually going to give us the exact area. But let's have a look at this general form, because when you look at the general form of Simpsons rule, it doesn't look quite so neat as what I've got written there. So what's going on? I can create more columns, or regions if you like, and then what do I do with that? What happens with these coefficients? Well, let's have a look. If we grab the first bundle, we would have just done x0, x1, x2. And then if we do the second bundle, like we did on the previous calculator screen, we'd add those two things together. Well, what happens when we do? Well, h over 3 is a common factor, so that can remain out the front. So we just have to add the bits in the parentheses. And when we do that, we get 2 servings of x2. One of our first one, x0, one of the last one, and these middle terms seem to have a 2 in them. And either side is a 4. So in general, what we get is we're adding up multiple regions. We get one of the first, one of the last, and then it alternates 4, 2, 4, 2, 4, 2, where it's 4 servings of the odd terms and 2 servings of the even terms. That's another way you might see Simpsons rule written. But could we do all of that simply on the calculator and get a really good approximation without having to use rectangles and trapeziums? Well, of course we can. So let's do a more general form of Simpsons rule, and I'll put that in g of x, and what I'll do is I'll just do our width 1, and I'll store that in our trusty friend d. D being the distance between each little interval. Let's go into table, and I want to edit my functions. So we'll leave f of x the way it is, and g of x, I'm going to say, in general, is d, remembering we don't have a h on the calculator, so I'm just swapping out the h for a d, d over 3 times bracket f of x is our first one, plus 4 servings of the next one, which is x plus d, plus 1 serving of the next one, which is x plus 2d. Close the bracket for f of x, close the bracket for our collection of terms, and press enter. Now, instead of doing it in a table this time, I'm actually going to do it in a list. So press data, and here I'll put 0 and 2, just so you can see what we did on the calculator screen before. And in this column here, I'm going to work out the area from 0 to 2, in other words d equals 1, and then the next one would be from 2 to 4, again d equals 1. So if I press data, I can go across to formula and edit the formula, and I'll choose G of list 1. And you can see the first value that we calculated previously was 2 over 3, and the second one 14 over 3, and the sum of them 16 over 3. Now if I wanted to make those intervals a bit smaller, and of course it's not going to make any difference to our result, it's kind of handy because it's a quadratic, but let's make an interval size of 0.5. So I'll quit out of here, and I'll store 0.5, oops, not too many, I'll put 0.5 and I'll store that in D. Now in my table, and I could get it to automatically calculate the list 1, but I can just type those in for now. 0, 1, remembering our width is 0.5, so therefore we do f of 0, f of 0.5 and f of 1, and then we'll do f of 1, f of 1.5 and f of 2 and so on. So I'll go 1, 2 and 3. Now I don't include 4 because the last calculation we're doing for our area is f of 3, f of 3.5 and f of 4. So let's check. I've got 4 values. You may have noticed they're automatically updating in list 2 here. So I've done f of 0, f of 1, f of 2, f of 3, or sorry, g of 0, g of 1, g of 2, g. Let's see what happens if I sum all the values in list 2. If I go to data, I can sneak back to operations by pressing the left arrow, and down the bottom of that is this really cool option to sum up a list. And I want to sum the values in list 2. And look what it's given me, 15.333, which is 16 over 3, the exact area that I got before. But I've just used more columns. So the beauty of this now is that if you wanted to change the function in f of x, everything will be recalculated for that new function. Now, could we do that with our trapezia and rectangles that we're doing before? Well, of course we can. So let's go back. We'll go back to our right-bound rectangles. We had 4 of them before. If I decided to get a slightly better approximation by having, let's say, 8 rectangles, that's a better approximation than what we did in the first place. The excess area is not as big as what it was before. But we can't use that summation tool anymore because it increments by 1 automatically. We can't control that. So now our increments are in steps of 0.5, but we can do the same thing again. So remembering, we're still doing height by width. So let's go back. This time I might use a sequence command to generate the numbers that I want. So let's go back to our calculator and see how we would do that. So I'll go into data, and because I'm going to start afresh, I'll press data again and we'll clear all those lists off. Now we want to go from 0 to 4, let's say, and we'll neaten that up in just a moment. So I'll choose data, go across to operations and choose option 3, which is sequence. I'm going to store my sequence of values in list 1, and my formula is just simply x. I'll start at 0, end at 4, and I'll make the step size 0.5, and then generate the sequence. And you can see it's just populated list 1 for me. It saved me typing it all out. In list 2, I need to calculate the height of each rectangle. In other words, f of 0, f of 0.5, f of 1, f of 1.5, and so on. So in this case, my formula is pretty simple. I'll go data, across to formula, and I'll add or edit the formula that I want for list 2, and it's simply calculate the height of each rectangle according to the values that are stored in list 1. So there's all my rectangle heights. So I need to sum all of those values up and multiply it by the width of each rectangle, which is, of course, 0.5. So let me just quit out of there. Oh, now, here's where we need to be careful before I quit out of there. Remember, for these rectangles, if I'm using, in this case, the left-bound rectangles, I don't include this last value. The last rectangle height is defined as 3.5. So let me just delete that one off. Notice list 2 automatically updates. So let's work out the sum of list 2. Sum of list 2. And I'm going to store that value in A. Now, of course, that's the sum of list 2. It's not the area. So if I quit back to the home screen, I would now do A. Oops, went too far. Let's try again. A times 0.5, which is the width of each rectangle, and I get 4.375 left bound. Not surprising, it's an underestimate. Let's go back to our lists, and of course for the right bound rectangles, we skip that first one, press the up arrow, put in the last rectangle, and again everything gets updated automatically. And now remember, I did the sum, so we'll go across to sum the list 2, and this time let's store the result in B. And I need to do B and multiply it by the width of each column, 0.5, and I get an approximate area of 6.3, and of course the area for the trapeziums is just the average of those two results. So I get that one plus that one and divide by 2, and I should get something pretty close to 5.3, and lo and behold I do. It seems like a lot of work, but the beauty of this approach is, what if I wanted to do even more columns and get a better approximation? Because the more columns that we do, the better the approximation. Now, I know Simpsons rule has given us an exact value at the moment, but that's just because it's a quadratic. I mean, in general, it does give you a better result. But let's go back in here because there's some nice practical results in here. So I want to change the step size here, let's say to 0.1. That's a lot of rectangles. That's like 40 rectangles that we're doing, but the calculator is going to do it pretty quickly. Now, remembering I went data, I go across to generate a sequence, and in this case, I'm going to store the sequence in list 1. I'm still using the same sort of formula, but this time I'm doing a step size of 0.1. Now, the beauty of this is, when I do sequence fill, I've still got all the heights being calculated straight away. So I've got in the left hand side x equals 0, x equals 0.1, x equals 0.2, and on the right hand side in column 2 I've got all of the heights automatically calculated. Now remember, I need to get rid of that very last one if I'm doing our left bound columns, and I need to do the sum of all of those values, all 40 of them. So let's go across to ops, sum, and we'll do the same approach, sum of list 2, and we'll store that in A. So that should be our smaller result, but don't be scared, it's not 51, it's 0.1 times 51, so 5.13, pretty close to what we know as our area. And now we can go back over here, add in our 4. Technically, I need to get rid of the 0, even though it's a height of 0, it won't make any difference to this calculation. Press data, and then we need to sum that list. And we stored it in B. And now if we go back to the home screen, our left bound rectangles, 0.1 times what we stored in A. So approximate area, 5.13. 0.1 times the value that we stored in B. So our outer bound, or right bound in this case, 5.5. And again, if I average those two results, that one and that one, divide by 2, and I get 5.33, which is pretty good. It's very close to our known area as 5.333 recurring, or 16 over 3. So that's a really quick way to do the area under a curve. We can use our summation tool if the width is 1. For anything smaller than a width of 1 or anything different than a width of 1, you want to use the lists. So our approximate area under curve, we ticked off quite a few boxes there, or rectangles. The natural summation tool is very good. Combined with the function notation, we were able to efficiently explore a decreasing width or interval, and we can compare the different approximation methods. Remembering Simpsons rule basically fills in the gap instead of with a straight line, but a quadratic. So expect it to give some pretty good results. It's just the formula's a little bit more difficult to work with. Finally, let's have a look at limiting sums. We'll explore some geometric series and some really weird functions called Taylor polynomials. And then we'll have a look at the convergence or divergence of the harmonic series. So let's start with a really nice example. A geometric series, we'll do it visually, that is 1/2 plus 1/4 plus 1/16 plus 1/32. So we're just doing half the remaining area of this object each time. And that looks like our expression here, 1/2 plus 1/4 plus 1/16 plus 1 on 32, plus 1 on 64, plus 1 on 128, plus 1 on 256, plus 1 on 512, and so on. I think we can see from the visual that it seems to be approaching 1, that we're eventually going to fill up that whole square if we went to infinity. So what we're looking at here is what is the sum of the numbers from x equals 1 to infinity of 1 over 2 to the power of x, because that's 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, and so on. Can we do that on the calculator? Well, let's have a look. We know where the summation tool is. That's in here. So I'll grab the summation tool, and I'll go from 0 to 8, kind of like an infinity on its side. Of course, it's not infinity. And we want over here 1 over 2 to the power of x. So we see that I don't want to go from 0, I want to go from 1. I've got too many terms in there. But we can edit it quickly. If you make a mistake, you can edit them quickly. And there it is. 255 over 256. That in itself was quite interesting. Let me just go back one term and let's do, say for example, oops, went too far. 2 to the 7 in the denominator. I think this is 127 over 128. There's a pattern going on here. What if I did to the power of 6? 63 over 64. We seem to be that one little fraction short. Now if you think about what was happening in our diagram, the bit that's missing here is 1 over 512. So it's no wonder when we add up all of those bits that we're just at 1 over 512 short of it. So 511 over 512 we'd expect to see in there. So in general, I think it's fairly clear that as x approaches infinity will equal to 1. And there's various ways we could prove that. Let's have a look at another type of series. This one is the one where we get our functions defined. So an infinite series, 1 over 0 factorial, which happens to be 1, 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, on forever. I wonder what that number is. Now we know that the denominator in this case, 1, 1, 2, 6, 24, 120, 720, 5060, these denominators are getting huge, which means our fractions are getting small very, very quickly. I wonder what that value is. Well, we can express that going on to infinity again. We'll use 8 on its side again. So from 0 this time through to some very large number, 1 over x factorial. I wonder what that number is. Let's have a look and see if that approaches some value. So let's try that on the calculator. We remember where the summation tool is. And we want to go from x equals 0. I'm going to go to 7 because that's what you had written on the screen. And we want to calculate 1 over x factorial. Our factorial key is a multi-tap key right here. And press enter. 2.7182. Now some of you may recognize that number. Not entirely, but at least the first couple of digits. There's a transcendental number called E, or Euler's number. They look remarkably similar. Let's have a look and see if I add up more terms, because I'm interested what happens as this value gets bigger and bigger. The amount that we're adding on each time is getting smaller and smaller. 1 over 10 factorial. 10 factorial is huge. So 1 over 10 factorial is incredibly small. So we get 2.71828110. That looks almost identical now to this value. In fact, if I go out to something like 12 or 13, I'm pretty confident these two numbers are going to be, as far as we can see, the same, certainly within the accuracy of the calculator. And look at that. So what? So what does all of that mean? Well, e to the x, not just e to the 1, is defined as x to the power of n over n factorial summed from n equals 0 through to infinity. So when we were doing our first calculation, we were just doing e to the 1. So x to the n just became 1 to the n, which is 1, 1, 1 each time, and n factorial in the denominator. So why would we care? That says e to the x, and that's it expanded instead of using the summation tool, and I think you can see the pattern. What's that got to do with, let's say, calculus, our topic, the idea of limits? Well, let's differentiate it. We want to differentiate e to the power of x. So to differentiate e to the power of x, the derivative of 1, I'm doing each term one at a time, the derivative of 1 is just 0. The derivative of x is 1. The derivative of x squared over 2 factorial would be just 2x over 2 factorial, and we could actually simplify that. The 2 factorial would just become 2, so those 2's would cancel out to have 0 plus 1 plus x. Maybe that's starting to look familiar. And if I look at the next term, that becomes 3x squared over 3 factorial. The 3 cancels the 3 factorial down to, in fact, 2 factorial. So we get x squared on 2 factorial. The next term becomes 4x cubed on 4 factorial. We can simplify these to get x cubed on 3 factorial. So, recapping, we have 1 plus x squared on 2 factorial plus x cubed on 3 factorial. And so we continue x to the 4 on what will be 4 factorial plus x to the 5 on 5 factorial. We get the same thing back again. So in fact, the derivative of e to the x, if we identify e to the x as being this Taylor polynomial, we see that its derivative is just e to the x. Let's have a look at a different one, a different Taylor polynomial. These things are really cool. So there's a function sine x. Can that really be expressed as a polynomial? Well, let's have a look at a cubic function. And we'll just focus on the first quadrant. Don't worry about too much of the rest of it. And I'll make that equal to x minus x cubed on 3 factorial. It's a really simple cubic. Let's see how close it matches sine x, just in the first quadrant. We can see through here, those values are very, very close. We can't see daylight between the function, our cubic function, and sine x until we get up to something pretty close to pi on 2. Notice we're dealing in radians. So what if I up the ante a bit? What if I do a polynomial, let's say degree 5? Well, Taylor's polynomial says, let's try x to the power of 5 on 5 factorial. Then that looks like that. Now, again, we're getting an even better approximation. It's that they look as though they're the same thing through here. And here, they're looking remarkably similar. It's only once we get outside this first quadrant. But of course, the more terms that we add, the closer and closer this thing becomes to the graph of sine x. For us, however, we know that between 0 and pi on 2, that first quadrant just gets recycled again and again through a series of reflections or dilation, or rather transformations. So let's define a function x minus x cubed on 3 factorial plus x to the 5. I think you could probably have a guess at what the next term is. It's going to be an x to the power of 7, right? It's probably alternating between negative and positive, positive, negative, positive, negative. So negative in here, x to the 7 over 7 factorial plus x to the 9 over 9 factorial and so on. We're just going to do the first 3 terms of our polynomial. So I'm going to change my function in here, and we said it was equal to x minus x to the power of 3 over 3 factorial plus x to to the power of 5 over 5 factorial. And that's it. That's all we're doing. We could actually use a summation tool and get even more terms, but that's all we need for now. So press enter to make sure I lock in my function. I don't need g of x, so I can now exit out of here. The one other thing that I do need to do is change my degree mode to radians, because this polynomial works in radians. So let's go ahead and do that. Press enter, and then we can quit out of there. And let's do a calculation. We'll just choose some value in that first quadrant at random. Let's say sine of pi over 3. And we get root 3 on 2. Let's do that approximately 0.866. Well, let's evaluate f of pi on 3. F of pi on 3. So correct to almost 4 decimal places. Our simple polynomial degree 5 is getting us estimates for sine of x. So going back to that, we could use calculus to work out the derivative and see if we could figure out perhaps what function the derivative might be. Now, one more series, because we're just about out of time, called the harmonic series, 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on forevermore. Now again, each one of these terms is getting smaller and smaller, so it'd be reasonable to say that it's probably approaching a limit. Let's try it on the calculator. It's a really easy sum to do. So I'm not going to define anything this time. I can just go straight into calculate the sum from x equals 1 to, let's say, 10 of 1 over x. So that would give us 1 over 1 plus 1 over 2 plus 1 over 3 plus all the way through to 1 over 10. And we get 2.982. So let's change that. And let's increase that 10, let's say, to 50. So 1 over 1 plus 1 over 2 plus 1 over 3 all the way through to 1 over 50. Now 1 over 50 is pretty small, so we're not expecting a massive change in this number. That's 4.5 roughly. I wonder if the thing is approaching 4.5. Let's find out. Let's go all the way through to 100. It could take a little while for the calculator to do this because it's doing a lot of number crunching here. The little hourglass spins around in the top right hand corner. It's jumped up to 5.187. So it's not really clear what or if that limit might be. So here's where we need to do some maths a little bit beyond what we're doing on the calculator. We're questioning, do these terms, successive terms, as they get smaller, are we converging? So what we're doing is we're wanting to know is if the sum from x equals 1 to infinity is some defined value. And for that, we're going to go back and do some calculus. Now, here's a graph of 1 over x. So this is what a width of 1 and a height of 1 might look like. That would be one lot of, if I'm working out an area, one lot of 1 times x, or 1 over 1 times 1 rather. If I add the next column in, again it's a width of 1, but it's a height of a half. So one lot of 1 over 1, one lot of 1 over 2, and of course you can guess what the next one is. It's one of 1 lot of 3, so the ones can come out the front, not that they make any difference to our sum, and we get left with 1 plus a half plus a third plus a quarter plus 1/5 plus 1/6 plus 1/7, and on forever. Now, remembering we said these ones, and because of our curvature, these left or outer bound rectangles in this case, will give us an overestimate for the area under the curve, or the approximate area, an overestimate. In other words, the sum that we're doing will be bigger than the actual definite integral of this function from 1 to infinity. of 1 over x. So all we need to know is, what is the integral of 1 over x? Well, it's the natural log of x. So we really want to do the natural log of 1 and the natural log of infinity and find the difference to get, well, the natural log of infinity is undefined, it's huge, it's infinite in itself. So in actual fact, this little bit of calculus can jump past a lot of number theory to prove that this limiting sum is in fact undefined. It doesn't converge at all, it diverges, it heads off to infinity because it will naturally be bigger than the integral from 1 to infinity, and that is a good place to stop. So, this beautiful little calculator is approved for HSC exams in New South Wales. And thanks for joining us.